So today we'll be talking about the concept of significant figures, or sig figs. Sig figs is a proper way to account for and address uncertainty in measurements, because in any measurement, the last digit is always uncertain, meaning that it's a rounded estimate of the actual quantity. So to better illustrate this, let's take for example that the mass of a substance measured on a scale is 4.72 grams. So this scale, we see, measures to 3 sig figs. However, if you have a less accurate scale, it might only show 2 sig figs, leaving you with 4.7. And if you have an even less accurate scale than that, with 1 sig fig, you might just see 5. Now, it's obvious that the mass of the substance didn't change between these 3 weightings. However, because this scale can measure to 3, this scale can only measure to 2, and this scale can only measure to 1 sig fig, the last digit is always uncertain, meaning the 7 is a result of the rounding down of the 2. The 5 is a result of the rounding up of the 7. So maybe the mass of the substance is actually 4.721 grams. But since this scale can only measure to 3 sig figs, the 1, therefore, is rounded down, leaving you with just 4.72. Now, there are a few basic rules to take in consideration when you're determining the amount of sig figs in any given measurement. The most basic and easiest rule to remember is that any non-zero number, regardless of their placement with the decimal point, is considered significant. So if you have 42.3789, because these are all non-zero numbers, they are all significant, leaving you with 6 sig figs. However, if you have zeros at the end of a number that are after the decimal point, like so, they're also considered to be significant, because this shows that the device you're using can measure accurately to the 10,000ths place. Zeros that are in between non-zeros are also considered to be significant, regardless of the place of the decimal point. So even if it was like this, you would still say that this quantity has 6 sig figs. As long as the zeros are bounded by non-zeros, they are significant, as long with the rest of the non-zeros. Now, there are a few cases where the numbers are not all significant. So, if you have 42,000, there's zeros at the end of the number that do not involve a decimal point, they are insignificant, because 42,000 in scientific notation can be written as 4.2 times 10 to the third, or to the fourth. Therefore, 4.2, 2 sig figs, leaving your whole quantity of 42,000 with just 2 sig figs. Zeros before a number are also insignificant. So in this quantity, these zeros are insignificant, because this can be written as 4.2 times 10 to the negative third. Therefore, 2 sig figs. So any non-zero number, whether before or after a decimal point, is significant. Zeros at the end of a number that are after the decimal point are also significant. 0 in between non-zeros are significant. However, zeros at the end of the number that do not involve decimal points are insignificant, and zeros before a number are also insignificant. Now, when you're asked to do operations that involve sig figs, such as adding or subtracting, there are a few basic rules to keep in mind. Now, for adding and subtracting, it's a little different, because you don't exactly consider the total number of sig figs, but rather the amount of places after the decimal point that the quantities are measured to. So given this equation, we can all agree that the total sum would be 40.63. That's excluding sig figs from the picture. But if you were to include sig figs in an addition problem, you would have to see which number has the least number of decimal places after it. So the 20.13 has 2, and the 20.5 only has 1. Because the 20.5 only has 1 number after the decimal point, your answer can also only have 1 number after the decimal point. Therefore, the 3 rounds down to leave you with 40.6. The same rule will apply for subtraction. So if you were to subtract these two numbers, we can all agree that the difference would be 0.37. But again, because 20.5 only has one place after the decimal point, your answer can only have one place after the decimal point. Therefore, the 7 rounds up and leaves you with 0.4. So when adding or subtracting, the key thing to consider is number of places after the decimal point. The number with the least number of decimal places, number of numbers after the decimal place, like here, there's only 1, will determine the amount of numbers after the decimal point that you can have here. Therefore, 1. Now, in multiplication and division, it is a little different because then you actually take into account the total number of sig figs, not really just the numbers after the decimal points. So, in 2.00 times 4, we can all agree that the answer would just be 8. However, in this case, it cannot be 8.00 because 4 only has one sig fig. 2.00, because the zeros are after a decimal point, has two sig figs. Has 3 sig figs. But because 4 only has 1, your answer can only have 1 sig fig. The same thing applies for division. So if you have 8 divided by 4.000, we all agree that 8 has 1 sig fig, and 4.000 has 4 sig figs. However, because 8 only has 1 sig fig, your answer, therefore, can only have 1 sig fig, leaving you with just 2, not 2.000, because 1 sig fig and 1 sig fig. So for multiplication division, the key thing to remember is the number of the least amount of sig figs determines the amount of sig figs that can be in your answer. Now, sometimes you're given exact measurements in certain problems. Say, for example, the temperature of a beaker is 35 degrees Celsius. If you were to do anything to 35, whether add or subtract or multiply or divide, that has to consider sig figs. As long as the 35 is an exact quantity, and the problem will say exactly 35, whatever, you don't have to take this into consideration with sig figs, because the last digit here, the 5, is not uncertain. We know for sure that it's exactly 35. There's no 35.1, it's just exactly 35. Therefore, when you do any kind of operation, you don't have to take into account sig figs for your exact numbers. Now, there's one more rule that has to do with pH and pOH measurements. So let's just say, for example, a number 12.345. If this was a regular number, we would say it has 5 sig figs. However, if this was a pH or pOH, it technically only has 3, because the numbers after the decimal point don't count. So even if it was 2.345, again, 3 sig figs, because numbers after the decimal point don't count. Now, commonly you're asked to calculate your pH or pOH from a hydroxide or hydronium ion concentration. So if you have 0.00100 as your, say, hydronium ion concentration, and you were asked to calculate pH, everybody would know that it'd be 3. However, because there are 3 sig figs here, your answer must also be written in 3 sig figs, leaving you with 3.00. Now, these special set of rules only apply to pH and pOH related calculations. If you're just adding or subtracting weights, numbers in front of the decimal point, as long as they're non-zero numbers, do definitely count. So as long as you keep in mind the basic rules of sig figs, you can create any kind of calculation in an accurate and proper manner with regards to uncertainty and measurements.